Hi everyone, I'm Adil Sheikh from Group 15. Today I'm going to demonstrate our implementation of BitTorrent, which is a peer-to-peer file sharing application. My team members are Sindhu and Nikhilesh. Our BitTorrent application, we have used TCP protocol to implement. First, I'm going to run the program to show you how it looks, and then we are going to look into the logs to see what's actually happening in the background and try to understand that. So first, I'm going to quickly go into one by one and start the peer. Just give me a second here. This might take a little time because I'm doing it manually. Start at 1, 2, start 3. Okay, now I have to start 4, start at 5, and the last one. Okay, there's one more remaining, and the last one. Cool. What was that? Spelling mistake. Cool. So I've gone ahead and run all of the commands that I showed you previously, and if we see now that every folder has a like every peer has a folder now, and if you go into like all of them one by one, you'll be able to see there's this file called the file in all of the uh, peers. This will be there. So the next thing that I'm going to show is, as I said, I'm going to show the resulting log that got generated after running all the commands, and I'll take one log as an example, but it will be same for all the other logs. So let us go to the so this was our project, and like it ran all of the commands, and I got back, and then we saw that every one has like a log file and then a folder with the file that was shared. So before going, so let us take log 1001 as an example, and I'll try to explain what really happens in the peer-to-peer file sharing, this BitTorrent application. So as you can see from logs, it is first thing it does is, you can see here, peer 1001 is trying to make a connection to peer 1002. It receives a handshake message. So normal handshake consists of a handshake header, 0 bits, and peer ID. This is used for establishing connection in TCP. Okay, so this is used for establishing after successfully sending handshake and receiving. After sending a handshake, the next message that a peer gets is a bit fill message. After handshake message, a bit fill message is sent. Bit fill represents the total number of pieces it has. Here, the total number of pieces it has is nothing but if you check how many total pieces it is sending to any user, it is 67. This is normally calculated by the number of total size of the file by the piece size, each piece size. So here we got 67 by because if I show you the peer info, I mean the common config file, we have 2167705 divided by 327568, which is 67 pieces. And then let us go back to the log that we were seeing. Now we know what is handshake and bit fill. The next thing is, once the bit fill happens, the reply is whether so a bit fill is nothing but it represents the total number of pieces it has. Here the total number of pieces is nothing but as I said, 67. If a peer has no pieces, it will skip the bit fill, and to the response of the bit fill, the response of the bit fill will be interested or not interested. If the peer wants it, he will send it interested, and if it does not want it, then it will send not interested. At any instance, each peer shares pieces with with the number of preferred neighbors, that is 3 here, and one optimistic unchoker for every 5 seconds. It has to generate new preferred neighbors, and for every uh, for every like we can find how for every how much time it is going to find. If I go to the common config, so at every 5 seconds it is going to create the preferred neighbors, new preferred neighbors. It's going to calculate and find the new preferred neighbors, that is 3, and there's always going to be one optimistically unchoked pair, and that will be calculated every 10 seconds. Okay, so now if we go back to the log, we'll be able to see that next after a log, as I said, interested or not interested happens, and we now know how they, to whom they send the pieces. That is the number of preferred neighbors, that is 3, and one optimistic unchoke peer. The next thing that happens is, after a peer is unchoked, it will keep sending this pieces, and in response to the piece it will send a request, which peer, like after which piece it wants. So it keeps sending it here, as you can see, and it has established connection with 1001. Peer 1001 is making to 1005. It is parallelly creating new pieces and getting like sending pieces to those peers that want those pieces in which are in the list of its neighbor, as you can see, successfully sending. So it has peer 5, piece 5, piece 13 it is sending. And then if you observe somewhere around here, it is showing 1007, which means it has find someone new. Here, as you can see, 1002 was unchoked, which means 1002 was the new preferred neighbor. And it's also sending half message. Half message is what, like, it consists of the piece indexes which this peer has, and peer 2 will respond if it is interested or not. Again, um, peer 1 receive, so it seems that it was interested and it wants to get those files. So those files were sent, and this keeps happening. Keeps happening with many different peers. And after some time, if all of the peers have completed downloading the file, it just closes the socket and the connections. Now, if you observe, the same thing happens, and everyone keeps sending everyone else the pieces. And then once it has download completed, like, uh, 1001 already had the file before starting, so hence it does not have this log, because it didn't really have to download. It was just sharing it with people. Now, whenever a peer shares the code with the people, it's going to add it to the there's one peer info.cfg. It's going to set that as 1. So if you, as you can see, everything set to 1. The setting of 1, like, everything is set to 1, right? Even this is really important for the termination of the application, for the processes, because once all of the process peer IDs are set to 1, only then everything will, like, all of the peers will stop. For example, let us say 1002 is here and it is set to 0. Still all the other 8 peer processes will still wait for, peers will still wait for 100 to download it, and then only then they will close. So this is really important for termination. Let us go back to the logs. As I said, this is important because, uh, as you can see here in this line, all peers have completed downloading the file is actually checking if all the peers have downloaded the file by reading our uh, peerinfo.cfg class, and then it is writing those, only then it is closing all of its connections. And then observe one more thing. 1002 will have another message called has downloaded the complete file, which means that it has downloaded all of the file, like the whole file. And after that it won't stop, but it will keep checking if everyone has completed downloading the file, only then it will stop. If you similarly see in log 1003, it has completed downloading the file but has wait like from 36 to 50 for to close, because at 50 check that everyone had downloaded the file, only then it closed all of those connections. And then 1004, similarly you will see that it completed downloading the file, and then it will close. And similarly in 1005 you will see the same thing happening. All peers have completed downloading the file, close the connection. 1006 has something called, even 106 does not have the message has completed, like it itself, like for example 1002 had has downloaded the complete file log, but 106 won't have, because even at the start of the running this application 1001 did not have, did have the file already, so it didn't really, it was just sharing the file with everyone else. And then 1007 same, and similarly 1008 and 1009. Next, we will look into each class, how, like what are the classes that we have, and what, how do they contribute to the whole overall project of the. Okay, so the first class is the bitfill class. Bitfill class is really responsible, as I said, bitfill is one of the messages which is sent to the peer who has sent handshake message. After the handshake message, only then bitfill is sent, and the bitfill class is mostly responsible for like having all of the pieces, and then the total number of pieces it has, uh, like, and it will we can, using this class we can create an bitfill class and update bitfill class, compare bitfill classes, bitfill objects and stuff like that, encode and decode. This is really important for sending the bitfill class, bitfill object. And then we have common CFG class, which is nothing but it's storing common.cfg. Common.cfg has information about the number of preferred neighbors that we have, that are three, the number of seconds it will take new preferred neighbors, like it will calculate new preferred neighbors every 5 seconds, calculate optimistically unchoked peers every 10 seconds, the file names, the file name, the file size, the piece size, which is used for calculating the number of pieces that we are going to send. And next thing, that next class is constants class. So the constant class is normally just a basic static class for the different sizes of the messages and types. We have one mapping of all of those messages, like we have message choke, unchoke, interested, not interested, have, bit, field, request, piece. The next class is data message class. So the data message, as I said, there are different types of messages that we just saw in the constants class. This will create a data message. Like this is used for creating data messages of different types, and all of the data about the messages, such as the type, length, payload, is saved here. And then, as you can see, there are two constructors for creating a message with just type, or with just type and payload, because some messages, as I said, do not have a payload, and some messages do have a payload. And then we have encode messages, and then even some helper functions. Then we have a decode message function, which is used for creating decoding others data message. Then we have a wrapper around this message to just get the data message. And then we have rate comparator, which is going to compare two peer infos. Peer info is nothing but the information about the peers, like the peer ID, address, port, if it has file, if it was the first peer, what is it, what state it is in. The state here is nothing but defined by in what stage it is running in. It's really state is really helpful for shifting from data to choke, unchoke, and stuff like that. Uh, then we have different stuff here for about the peer info. And then the next thing here we have is a handler. A peer info handler is doing nothing but uh, this is also a really important class, because it also handles, creates active connection and passive connection with the peers. As you can see, we have an active, passive. First it's going to send the handshake, and if the handshake is successful, it's going to send the bit filled message, and then it's going to keep sending the data message. Okay, so this is really important for these three steps. And as you saw in the data message, there are different types of data messages. And then we have peer process. Again, peer process is another important, really important class, which which first of all is the starting point of our program. Every peer process starts with calling this class with the peer ID, and this class calls all the other classes that you have seen till now. Even it handles stuff like reading from all the configuration files, load like uploading it all to the all the like updating all the configuration files. And it is also responsible for things such as you know um, calculating the preferred neighbors, calculating the unchoked, optimistic unchoked neighbors, etc. And then we also, I think I missed a class here, yeah, message handler, which is going to handle the different data messages that appear receives. So the data messages, as said, are different. Half message, if it receives a half message, what it's supposed to do. Like every case is defined by each type of data messages, and then how to handle them is written here. And also this is the place where the state of the programs keeps changing. As you can see, process keeps changing. And then we have, after this, um, we've seen this, we have, okay, piece class is nothing but, as I said, the data is sent as pieces. So piece class stores the data, the if it is present or not, if like it's just a structure for defining each piece. And then we have thread for listening, which is really important for starting sockets, TCP sockets, and stuff like that. And yeah, this is the whole structure of our like classes that we've seen. And before that, we even saw how we can create like how to run the files. We saw the logs, how they were generated. One thing that uh, I want to mention is the program can vary based on the like there are some limitations of this project. First is that if you see here in the common.cfg, we need this common.cfg. There's not really, like in a real scenario, BitTorrent application won't really have like we don't, like the user won't be giving all of this information, but this will be calculated on its own. So that's one like limitation of our project, that it's not really a real BitTorrent application, because it's not doing all of this work like calculating the piece size, the file size, or the file name. And in a real scenario, you would have to dynamically create this. And then the other thing is, if the file size increases and then the pieces are really small, then it's going to take a lot of pieces to completely send the file. So the application should also dynamically like with an optimized algorithm find the piece sizes, how much piece size it should be, which our application does not do at all. It's going to be at fixed with this piece size. And the other thing, as you've seen, is the other limitation that we have seen is that we were not able to demonstrate start remote peers class. Like we have talked to professor about it, and the professor said that it was fine to demonstrate using manual SSH. That's what we demonstrated. And but we would have to work on that. There was some problem with the running start remote peers with Linux servers of our university. But I think yeah, that's one thing we had to do. But in reality, one more thing that in real BitTorrent application is present and it's not present is even start remote peers. um, like every user will be starting their own peers, and then it will keep sharing the file like to other people. So like we don't really have a torrent file here. It's, you've seen, there's nothing like a torrent file here. I would also like to mention that in the recording that we just showed you, we are showing .txt logs.
We observed this like after the recording, and then we have changed the code to print out like push all the logs in a .log file. So we have our current project will be outputting .log files. In overview, BitTorrent is a file sharing peer-to-peer program which does not need a server to save the files or to share the files. There's no need for a backend server or a database. This is achieved solely by different peers connecting to each other, sending handshakes to establish connections, and through sending the file through different messages asynchronously, like bit field request, have interested, etc., not interested, etc. The file is shared. We are. I would also like to thank for the support and cooperation from our Professor Yasha and teaching assistant Zio Shu. Throughout the semester, working on this project has helped learn the basics of computer network and TCP protocol. We also got to implement the whole program in Java. That was fun. With this, I'm going to end the presentation. Thank you.